For tuning in. My name is Christopher Jung from University of Pennsylvania, and I'll be talking about service in your neighborhood, fairness and center location, which is a joint work with Sampath Kannan and Lutz. First, I want to talk about the motivation of this project. So recently, there has been a lot of research in the domain of algorithmic fairness, but most of this algorithmic fairness literature has focused on supervised setting, meaning given a collection of data, which is in the form of feature and label, we want to produce a classifier that will predict a label given features. And the examples that this some examples this literature is concerned with include bank loan, college admission, parole and sentencing decision, and etc. One thing to kind of note among these examples is that these are very significant consequences, but there is a possibility of revisiting the decision. Now, we realize that there hasn't been as much work done in the unsupervised setting, such as clustering problems, meaning instead of having both feature and label as part of our data, only thing that we have is just simply the features. And the kinds of examples that we were thinking of are of infrastructural decisions, meaning we were concerned about where should we locate hospitals, schools, library branches, police or fire stations. And in contrast to the previous examples that we have seen, for these kinds of examples, once the decisions have been made, it will be much harder to revisit the decision. Hence, we thought that it is very significant that we think about fairness for these kinds of problems as well. We weren't the first people to think about fairness for clustering problems. There has been significant amount of fair clustering research that's been done, but we take a slightly different approach, which I'll explain next. Before doing so, let me first kind of have an overview of what the nature of clustering problems are. So clustering problems, we mainly think of it as given some n data points and k, which is the number of centers that we want to place. We want to come up with a solution S, which is basically location for these k centers, so as to minimize these different kinds of objectives. So for k-means, we want to minimize the sum of square distances. K-medians, we want to minimize the sum of distances. And k-center, we want to minimize the maximum distance. Where when I say distance, I mean distance from some point P of our data to its closest center that we have placed. And now let's think about fairness for these clustering problems. For supervised settings, a lot of fairness definitions are of equalizing some kind of measures, such as equalizing false positive rate, equalizing positive predictive value, and so on. The previous fair clustering literature bears a similar form in that it tries to have equal representation of groups across clusters. But we wanted to we take a slightly different approach in that we wanted to come up with a fairness concept that tries to take population density into account. And by doing so, we had two goals. We wanted to be the case that outliers do not disproportionately affect the final clustering outcomes. And we also wanted to be the case that clustering size will be roughly equal. And I'll talk about later why these two goals are of importance for fairness. And before doing that, let me first define this thing called neighborhood radius of some individual I, which is defined as the minimum radius of a ball centered at individual I to contain n over k individuals. So here's an example below, just to get some intuition. We have 10 data points denoted by these human beings here. And we want to place two centers, so n equals 10 and k equals 2. And let's focus on the person on the left. And I've drawn the minimum radius. I've denoted its minimum radius by the circle, which is basically how much this person has to travel from himself to contain to contain n over k, in this case 5 individuals. So what does that look like? What does neighborhood radius look like for the person on the right? Because this person is further away from the majority of the people, it's in this sparse area, its neighborhood radius is a lot bigger, meaning it has to travel a lot further to contain n over k individuals here. Now, given that, we want to find a solution such that each individual can find a center within his or her neighborhood radius. And unfortunately, guaranteeing that is impossible. So our goal is to optimize how far we deviate from this ideal. And to that end, we define alpha fairness. We say an algorithm satisfies alpha fairness if for every individual I, the ratio between the distance to its closest center and neighborhood radius is at most alpha. And our goal in this case will be to minimize this alpha, the maximum factor by which any individual's fair expectations are not met. And here are some justifications as to why we think that this is reasonable. First, people living in areas with different population densities have different expectations for a reasonable distance to travel to a center. Due to different population densities, people will have different amount of access to transportation, and hence, if you're in a rural area, it would be unreasonable for a resident to expect to find a hospital within a mile of the person's residence. Whereas in urban areas, that might be an entirely reasonable expectation. And second of all, this kind of balances load across centers. A hospital located in an urban area may be overcrowded compared to the ones in rural areas if you don't consider the population density into account when you're thinking of these clustering problems. But by considering population density into account through neighborhood radius, we're hoping the number of people served by each center will be close to each other. And in this settings, here are some results that we have. First, we can show that in any metric space, it has to be the case that any solution will have alpha greater than or equal to 1/2. And we also show that there exists a metric space such that no algorithm is alpha fair for any alpha strictly less than 2. And in the Euclidean space, we can show that the same thing for alpha strictly less than square root of 2. We also show an algorithm that achieves alpha equals 2 in any metric space, and later on we realize that there are similar ideas in the metric embedding literature. And as a corollary of the first result that says in any metric space alpha has to be greater than 1/2, and this algorithm achieves alpha equals 2, the corollary is that it is a 4 approximation algorithm. We also show that minimizing this alpha is actually NP hard. And finally, we show some empirical results by running our algorithm on 2 geographical data sets. And now I will go through some of our results and its proof. The first result that I'll go through is that any solution must have alpha greater than equal to 1/2. And here's the proof. So we know that there has to be one center, at least one center, where at least n over k points have that center as the closest center. And let's call that center S, and denoted by this red person. And within that cluster, we'll consider the furthest point P, denoted by this blue point, among those n over k points. And so we have this visualization above. We have this red point and all these people who have red point as the closest center. And blue is the point among all those n over k people who is farthest away from the center. And now let's consider a ball centered at this blue point, P, with radius twice the size of the distance from point P, the blue point, to the center, point S. And we know that because we chose point P to be the furthest point away from this red point, we know that this ball has to contain at least n over k points. And with that, we can actually show that the ratio between the blue point's distance to the center and its neighborhood radius has to be greater than or equal to 1/2. And which proves the results that any solution must have alpha greater than or equal to 1/2. And second result that I want to go through is that there exists a metric space where achieving alpha for alpha strictly less than 2 is impossible. And we prove it by this example. So we have these 3 squares. And the number of points that number of centers we want to place among these points is k equals 4. It's immediate that neighborhood radius of each point is 1. And also it's immediate that for any choice of centers, one of these squares will have at most 1 center. Because we have 3 squares, but then the number of centers we have is k equals 4. And let's consider that square where it has at most 1 center. Within that square, we know that there has to be at least 1 point which has to travel at least 2 edges to get to the center. And for that specific point, the alpha will be 2. So we know this shows that achieving alpha strictly less than 2 all the time is impossible. And in the Euclidean space, instead of this at 2 edges, this distance will be square root of 2. And now I want to go through algorithm that achieves alpha equals 2. And the algorithm itself is actually pretty simple, and the proof is very simple as well. So at each iteration, we choose a point S with the smallest neighborhood radius, and we place a center there. And as we do so, we remove that selected point S and all other points that fall within the neighborhood radius of that S. And we repeat this process until there's no point left. And here's a proof as to why this achieves alpha equals 2. We know that first, simply note that point S and the points within that neighborhood radius of point S have a center within twice the size of the neighborhood rate. It's their own neighborhood radius because we chose point S to be the one that has the smallest neighborhood radius. So every time we choose a point, and every time we remove any points, we know that they have alpha less than or equal to 2. And the second thing to note is that in each iterations, we're removing at least n over k many points. And so that shows that our algorithm uses at most k centers and achieves alpha equals to 2. And those are our theoretical results. And here's and we also ran our algorithm and have some empirical results. What we do is we run our algorithm and some vanilla k-means, k-medians, and k-center algorithms on 2 geographical data sets, where one geographical data set is the address points of Fairfax County, and the other one being address points for Allegheny County. The Fairfax County contains 537, 500, and 514 points, and Allegheny County contains around 370k points. And as I said before, the algorithm that we used are just vanilla algorithms for k-means, k-medians, and k-center. And for our algorithm, the bottleneck for the running time is finding the neighborhood radius. So we actually used KD tree to be able to calculate the neighborhood radius very fast. And for the rest of the talk, I'll show the visualization of those points and the centers, and then how these different algorithms compare for these different objectives. The objectives for like k-means, k-medians, where k-means objective is like sum of square distance, as we said before, and so forth for the other ones. And finally, I want to show the standard deviation of each clustering size, cluster sizes, where and this kind of shows that our algorithm does balances load relatively better than the other algorithms. So here's what the centers and the data points look like for Fairfax County, where the blue points are the original address points, and the red are the centers, 100 centers that's placed. So this is what it looks like for k-center on the left, k-means on the right, k-medians on the left, and our algorithm on the right. And this is what it looks like for Allegheny County. K-center on the left, k-means on the right, k-medians on the left, and our algorithm on the right. And finally, this is what the objective function for each look like for different algorithms. And you can see that fair k-center, which is our algorithm, has the lowest alpha among all the other algorithms. And even for other objectives, so k-means, k-medians, and k-center objectives, it doesn't do so badly. So things to note, you can kind of already tell from the visualization it tends to place more centers in denser regions compared to other algorithms, and it's kind of consistent with our intuition, as address points in dense regions tend to have smaller neighborhood radius. And kind of going back, it does kind of the worst for fair k-center does kind of the worst for the k-center objective. So the maximum travel distances increase significantly compared to other algorithms, but these large travel distances are experienced only by few residents of particularly sparse areas. And finally, here's what the table looks like for the standard deviation in cluster sizes, where cluster size is the number of points for which that center is the nearest. And you can see that in both data sets, fair k-center has significantly lower standard deviation in terms of its cluster size, meaning it does balance the load among centers relatively better than the other algorithms. With that said, here are some future directions that one can think of. One can kind of think about different neighborhood radius. So in the case of our neighborhood radius, we took inverse local population density as a proxy for the size of a neighborhood, but there might be a more sophisticated approach. And second, one can possibly consider allow Steiner points. So just by the nature of our algorithm, we always place a center on top of one of those data points, but we can possibly allow Steiner points by removing this restriction where you have to place a center on top of a data point. And finally, there is some looseness in the Euclidean space where we know that alpha has to be greater than or equal to square root of 2, and our algorithm achieves 2. Alpha equals 2, so it might be interesting to see if we can close this gap. With that said, thank you once again for tuning in, and thank you.